Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by SWAYAM. During this session, let's talk about PIPO and PISO registers. In the last class, we were talking about registers and we understood that they are sequential circuits containing flip-flops that are arranged in a chained manner. We saw the left and right shift registers and also the different modes of entering data to and exit from the registers. And in detail, we discussed about SISO and SIPO registers. In this class, you will be introduced the PIPO and PISO registers and we will learn about the concept of universal and bidirectional shift registers too. So, let us start with PIPO register. What does PIPO stands for? It is the parallel in, parallel out register. In the last session, we had seen that the term parallel signifies that the data is entering or exiting from the register simultaneously. Here, the entry and exit of data happens in parallel mode. Look at the logic diagram of a PIPO register and let us analyze how the values are shifted inside the register. Please count the number of inputs and number of the outputs to this register. There are 4 inputs, 1 to each flip-flop, and there are 4 outputs, 1 from each flip-flop. When you compare it with SIPO and SISO, the method of entry of data values into the register was different. There, the data was loaded in a serial manner. Here, the data enters in a parallel mode. And at the rising edge of the first clock pulse itself, all the 4 bits will be loaded into the flip-flop and will be available at the outputs. See how faster PIPO register is when compared to the other registers. Look at the table, you can see the contents of the flip-flop and the external outputs all are set in just one clock pulse. So, we can infer one point from this, that the parallel mode of operation is faster than the serial mode. And moreover, you can load and retrieve an n-bit data word in a single clock pulse. The number of clock pulses and the number of bits are not dependent as we had seen in the earlier shift registers. But all good things comes with some shortcomings. Here also there is an issue. The design of such circuits will not be that easy as the serial ones. Remember one point, there is an increase in the number of input and output pins, where in SISO and SIPO were satisfied with either one input or output pin. In PIPO, we need n number of inputs and n number of for an n-bit data word to be loaded and shifted in the register. One more important point, there is no left and right shifting in PIPO registers because the data is loaded and retrieved in parallel mode. Shifting is possible only in those registers which has a serial mode either in input or output operation. Let us move on to the last case, PISO, the parallel in and serial out register. Now, we are able to guess the number of inputs and the number of outputs in this register. Since the input is in parallel mode, to load the register with 4-bit data word, we need to have 4 input pins. And the output of data is in serial mode, which means that it needs only one output pin. Now, let us have a look at the diagram to verify whatever we assumed is right or not. See the logic diagram of the PISO register, it seems to be little intriguing. It is quite different from whatever we have seen before. Do you want to know why the logic diagram is not as simple as we had assumed? Let us dive into the details. For a PISO register, the data has to be loaded in parallel and the data needed to be shifted serially towards the output pin. You know that the parallel mode of operations happen in a single clock pulse no matter how big your data word is. So, in order to load this 3-bit data in parallel, you need to have 3 external inputs which you can see in the diagram as mentioned as DA to DC. After loading the data into the register, the values have to be shifted. To shift it serially, a flip-flop need to receive its input from the previous flip-flop. In that case, for a PISO register, each flip-flop requires 2 inputs, one from outside to load the data and the other from the previous flip-flop to shift the data. We cannot accept both the inputs separately because the D flip-flop only takes one input at a time. How should we fix this issue? The solution is we should design the circuit in such a way that it will receive one input at a time, whether it is external or internal. The additional gates that you see above the flip-flops in the diagram are used for that. They are nothing but the combinational gates which control the loading or the flow of the data. Remember, in the introductory session of registers, we had seen that the processing of data is controlled using combinational gates and the storing of data is done by the flip-flops. Now, let us see how these combinational gates help in achieving the task of receiving exclusive inputs to the flip-flop. Look at the diagram once again. You can see 2 AND gates, one receiving the external input and the other one receiving the serial input. There is one more signal down there called as shift load. This is the most crucial signal in the circuit which can be enabled or disabled. When the signal is disabled, that is when the signal is at a low level, then the AND gate which receives the negated input of this signal gets enabled. So, all the AND gates on the top becomes active when the shift or load signal is low, and it is highlighted in blue color in the figure. The AND gates below are disabled and produce an output 0 since the shift load signal is 0. This is the loading mode. Now, all the external inputs will get loaded inside the flip-flop. Once this phase is over, it moves to the shifting phase. For this, we have to enable the shift load signal. When the signal becomes 1, all the upper AND gates connected to the external input becomes 0 and the lower AND gates becomes enabled. Look at the diagram. Now, the lower AND gates gets enabled and this will trigger the shifting action of bits from one flip-flop to the other. See the figure. Now, the AND gates below are highlighted, indicating that shift operation is happening. We know that during the first rising edge of the clock pulse, the first flip-flop transfers its bit to the second flip-flop and the second flip-flop transfers its bit to the third, and the third one places the rightmost bit on the output pin. At the second rising edge, the same cycle of shifting takes place and it continues for the third rising edge too. Now, the 3-bit data word is available on the output pin. Look at the table which shows the state of the flip-flop at each clock pulse if the data word is 1010. The first clock pulse was enough to load the bits into the 4 flip-flops, and later by the arrival of the subsequent clock pulses, the values were shifted to the output pin serially. It took 1 clock pulse to load the data and 4 clock pulses to transfer the data. So, a total of n plus 1 clock pulses are needed in a PISO register to transfer the data across. One of the major advantage of PISO register is that it can be used to convert the parallel data to serial data. And this conversion is significant in the design of the digital systems. Now, we are done with the 4 modes of the register. Before we move on to the next type of registers, let us be thorough with the difference between serial and parallel mode of operation in registers. In parallel mode, the information is available in all the registers and transferred simultaneously to the output pins during one clock pulse. In the serial mode, the registers have a single serial input and a single output, and the information is transferred one at a time in a single direction. The direction could be either to the left or to the right. The computers can operate in serial mode, parallel mode, or in a combination of both. The serial operations are slower because of the time it takes to transfer the data in and out of the shift registers, but they require only less hardware to carry out these operations, hence very easy to design too. The parallel operations are faster compared to the serial operations, as transfer of data in and out of the register happens in one clock pulse. However, they need more hardware to perform these operations, and mostly the computers operate in parallel mode as it is the faster mode of operation. Now, we have learnt about the different modes of data transfer in shift registers. The next register we are going to deal is bidirectional shift register. These registers allow the shifting of data to the left and to the right. How is this possible in the same register? It is possible with some control logic built into the circuit. Along with that, for right shift, we need to have a serial input line attached to the leftmost flip-flop and a serial output line to the rightmost flip-flop. And for the left shift, a serial input line should be present in the rightmost flip-flop and a serial output line at the leftmost flip-flop. The control line decides to shift left or right depending on the input value it receives at any particular instant of time. The mode of operation for the input value will be decided at the design phase of the circuit itself. Look at the diagram. It has a control line called as left-right. As per this circuit, if that line is high, it will perform right shifting, else it will perform left shifting. You can notice in the diagram that the same input line is fed to leftmost and rightmost flip-flop to perform serial left and serial right operation. And there is serial output line exiting from the leftmost and rightmost flip-flop to serve as the output in the case of serial left and serial right registers. This is all about bidirectional shift register. They have the capability to shift to both directions, and if a register can shift to only one direction, then they are known as unidirectional registers. If bidirectional shift register can load and retrieve data in parallel, then we call such registers as universal shift registers because they can perform all four modes of operations in the same register. For such registers, we need to have n external input and output lines added to the bidirectional shift registers. Moreover, we need two control lines to choose among the four operations. Let us have a look at the universal shift register. The given diagram shows a 4-bit universal shift register. See, it contains the following components. There is a clear control to clear the register to 0 and is mentioned as clear in the circuit. Then it has the clock signal to supply the clock pulse, and to synchronize the operations of the register, it is denoted as CLK in the register. There are two input controls S0 and S1 to control the mode of operations of the register. We will see in detail about this soon. Next, it has serial input for the left shift and the right shift registers. The output line A0 forms the serial output of the register and A3 forms the serial input of the register. There are 4 parallel inputs I0 to I3 and 4 parallel outputs A0 to A3. Apart from all these, we have used multiplexers denoted as MUX. The multiplexer is a combinational circuit which allows us to select one input from a series of input lines and forward it to the output line. Here the multiplexers have two common input controls S0 and S1. Depending on their values, suitable operations to be performed on the registers will be decided. Then there are flip-flops also to store the values inside the circuit. Since we are using 4-bit data word, we need to have 4 flip-flops and 4 multiplexers to design the registers. These are the hardware components required to build a universal shift register. So, there are 4 control lines: clear, CLK, S0 and S1. Then 4 parallel inputs and 2 serial inputs. In the case of output, it has 4 parallel output lines and 2 serial inputs too. Other hardware include 4 multiplexers and 4 flip-flops too. So, now you are clear with the hardware used to build the universal shift register. Now, let us see the control operations. The clear signal is to clear all the flip-flops to 0. The clock determines the time at which the flip-flop stores the new bit of information, and it will help us to synchronize the operations of all the flip-flops. That is why all the flip-flops are connected with a single clock pulse. There are 2 more control inputs, S0 and S1. 2 such bits can have 2 raised to 2 combinations, that is 4 combinations altogether. Now, let us see the effect of each combination of values. Suppose S0 S1 equal to 0 0, then it indicates that no change happens to the register. It retains in the previous state itself. The present value of the flip-flop is applied to the D inputs of the flip-flops. As per the working of the D flip-flop, it retains the value as it is, resulting in a no change situation. If S0 S1 equal to 1 0, then the left shift operation will be triggered. The rightmost flip-flop should initiate the left shift operation. To inform this to the first flip-flop, the MUX selects the second input and passes it as the output of the MUX. The corresponding flip-flop will receive this input, and now the left shift operations becomes active. What if S0 S1 equal to 0 1? Then the right shift operation will be triggered. The leftmost flip-flop should initiate the right shift operation. To inform this to the leftmost flip-flop, the multiplexer selects the first input and passes it as the output of the multiplexer. The corresponding flip-flop will receive it and initiates the right shift operation. If S0 S1 equal to 1 1, this is an indication for parallel load. Then the binary information available at the parallel inputs are stored into the register and made available at the parallel output at the same clock pulse. This is shown as a function table in the diagram. This register is a general purpose register capable of performing 3 major operations: shift left, shift right and parallel load. In addition, it retains the previous value of the circuit in the memory as its 4th operation. Now, we learned about the important types of registers used in the digital systems. Let me tell you a little more about the applications too. Shift registers are primarily used in arithmetic and logic unit ALU to perform arithmetic and logic operations. They are used as temporary memories and for shifting data to the left and to the right during these operations. Shift registers are also used for changing serial data to parallel and parallel data to serial. These registers also find application inside the calculators too. Before we wind up, let us have a recap on whatever we discussed so far. The registers are sequential circuits which can perform in 4 different modes. serial in, serial out, serial in parallel out, parallel in parallel out, and parallel in and serial out. Then we learnt about the bidirectional shift register, which can shift data to both directions. At the end, we learnt about the universal shift register, which is general purpose register. In the next session, you will be introduced to a special type of register called as counter, which is capable of counting and retaining the count. Thank you for watching. See you in the next session. Bye.